If you were an aerospace engineer tasked with designing a planetary life support system from scratch, built for maximum durability and efficiency, you would not design Earth. While we view our planet as a biological paradise, the data suggests otherwise. Biologically speaking, Earth is surprisingly hostile. More than 30% of our surface is barren desert or ice caps. Our star, the Sun, is volatile and burns through its fuel too quickly. In terms of planetary engineering, Earth is not the gold standard. It is merely a functional prototype. This leads to a critical question posed by astrophysicists. Is there a better blueprint for life? In 2020, a landmark analysis by researchers Schulze-Makuch, Heller, and Guinan challenged the Earth-Centric Bias. They introduced the concept of super-habitable worlds, planets that are not just capable of sustaining life, but are statistically engineered to support more biomass, greater biodiversity, and endure for billions of years longer than Earth. Before we begin, please consider subscribing to support this channel's research. Now, let's get started. To appreciate the radical nature of the super-habitable theory, we must first contextualize the rapid evolution of exoplanetary science. For the majority of the 20th century, including the era of the Apollo program and the Space Shuttle, the existence of planets orbiting other stars was a statistical probability, but an unproven hypothesis. It was not until 1995 that Michel Mayor and Didier Queloz confirmed the existence of 51 Pegasi b, the first planet discovered orbiting a sun-like star. This discovery, which later earned a Nobel Prize, shifted exoplanetary science from theoretical philosophy to hard data. Following this, the launch of NASA's Kepler Space Telescope in 2009 provided a census of our galaxy. We moved from knowing 0 exoplanets to confirming over 5,500 candidates today. Initially, the search followed a simple heuristic, the Earth analog approach. Astronomers hunted for a planet of Earth's size, orbiting a G-type star like our Sun within the habitable zone, the narrow orbital band where liquid water can exist on the surface. However, this approach suffers from a logical fallacy known as the anthropic bias. We assume Earth is the biological optimum simply because we are here to observe it. But the geological record tells a different story. Throughout its 4.5 billion-year history, Earth has been largely uninhabitable to complex life. It has swung between snowball Earth scenarios, where ice reached the equator, and hothouse periods of extreme heat. Our planet has endured 5 major mass extinction events, several of which nearly reset the biological clock entirely. From an engineering perspective, Earth's life support systems are fragile. The concept of super-habitability, formalized in the 2020 study led by Washington State University and the Technical University of Berlin, argues that we should look for worlds that correct these flaws. A super-habitable planet is defined by 3 specific engineering criteria superior to Earth's: thermodynamic stability, a climate that fluctuates less, preventing rapid glaciation or runaway greenhouse effects; biological capacity, a surface environment capable of supporting a higher total biomass, more life per square mile. Temporal longevity, a system that remains stable for a time frame significantly longer than the Earth-Sun system allows. As we analyze the data, we find that the perfect planet does not look like Earth. It looks like an older, more massive world orbiting a different kind of star entirely. If you are finding value in this analysis, please take a moment to click the like button. It supports the channel significantly. Thank you. To evaluate the habitability of any planetary system, we must first analyze the engine driving it, the star itself. Our Sun is a G-type main-sequence yellow dwarf. For decades, astronomers assumed this was the ideal classification for life. However, from a stellar engineering perspective, G-type stars possess a critical design flaw. They burn too bright and die too young. The Sun has a total lifespan of approximately 10 billion years. We are currently about 4.6 billion years into that cycle. While this sounds like ample time, the habitable window is closing much faster than the star's actual lifespan. As G-type stars fuse hydrogen into helium, their core density increases, causing the star to burn hotter. According to stellar evolution models, our Sun's luminosity increases by about 1% every 100 million years. In approximately 800 million to 1 billion years, the Sun will be 10% brighter than it is today. This increase in solar output will trigger a runaway greenhouse effect on Earth, boiling off our oceans and effectively sterilizing the biosphere long before the Sun ever expands into a red giant. In cosmic terms, Earth is already in its final biological chapter. If G-type stars are too short-lived, astronomers initially looked to M-type red dwarfs. These make up 75% of the stars in our galaxy and burn their fuel with extreme efficiency. They are capable of shining for trillions of years, providing a time window for biological evolution that exceeds the current age of the universe by orders of magnitude. However, data from the Kepler mission and ground-based spectroscopy has revealed that M-dwarfs are likely hostile to life. Because they are so dim, a planet must orbit dangerously close to maintain warmth. At this proximity, the planet becomes tidally locked, one side facing the star forever, the other frozen in eternal darkness. Furthermore, M-dwarfs are prone to violent magnetic flares that can strip a planet's atmosphere in a matter of hours. This brings us to the prime candidate for a super-habitable system, the K-type orange dwarf. K-type stars sit in the evolutionary sweet spot between the volatile, short-lived Sun and the dim, dangerous red dwarf. They offer three distinct engineering advantages. Optimized lifespan. K-type stars have main-sequence lifespans ranging from 20 to 70 billion years. This is 2 to 7 times longer than our Sun. This extended timeline is critical because evolution is a slow process. It took Earth nearly 4 billion years to produce complex animal life. A planet orbiting a K-star would provide evolution with tens of billions of years of stability to refine biological systems. Radiation stability. Unlike red dwarfs, K-stars are calm. They emit significantly less ultraviolet UV radiation than young G-type stars and suffer fewer magnetic outbursts than M-types. This reduces the strain on a planet's ozone layer and DNA integrity. The Goldilocks spectral peak. K-stars peak in the infrared and near-infrared spectrum. This light is gentler, but sufficient for photosynthesis. In fact, plants on a K-star world wouldn't be green. They would likely be yellow or red to maximize absorption of this specific light spectrum, creating a biosphere that is distinct but highly energetic. If we are looking for a star system designed for the long haul, the Toyota Camry of the galaxy, rather than the high-performance, short-lived sports car that is our sun, the K-type orange dwarf is the superior choice. Having selected the engine, the K-type star, we must now design the hull, the planet itself. The data indicates that Earth is slightly undersized for optimal habitability. A super-habitable world would likely be a super-Earth, a planet with approximately 1.5 to 1.6 times the mass of Earth and a radius about 10% to 20% larger. This additional mass is not merely for surface area. It is a requirement for geophysical longevity. The most critical life support system on any planet is its carbon silicate cycle. This is the planetary thermostat that regulates atmospheric carbon dioxide over millions of years. This cycle requires active plate tectonics, driven by the heat of the planet's molten core. Earth's core is cooling. As it cools, tectonic activity will eventually slow and seize up. When plate tectonics stop, the magnetic field generated by the geodynamo collapses, and the atmosphere is stripped away by solar wind. This is exactly what happened to Mars. A super-Earth, with its greater mass, acts as a heat battery, retaining its internal thermal energy for billions of years longer. This ensures a strong magnetic shield and an active thermostat long after Earth's core has solidified. From a biological perspective, we must also consider surface topology. A common misconception in sci-fi is the water world, a planet covered entirely by deep oceans. While such worlds exist, they are likely biological dead zones. Life requires nutrients, like phosphorus, which come from rock erosion. Without exposed land, the nutrient cycle breaks. The optimal design is not deep ocean, but shallow seas. We are looking for an archipelago world, a planet with widely distributed island chains, rather than massive, arid supercontinents. Shallow waters allow sunlight to reach the seabed, creating vast regions similar to Earth's continental shelves, which house the majority of our marine biomass. A slightly warmer planet, about 5 degrees Celsius or 9 Fahrenheit warmer than Earth, would eliminate ice caps, raising humidity, and creating a global environment akin to a temperate rainforest. However, no design is without trade-offs. While a super-Earth is superior for biology, it poses a severe challenge for technology. The same gravity that retains a thick atmosphere and protects life creates what aerospace engineers call the gravity trap. Spaceflight is governed by the Tsiolkovsky rocket equation. On Earth, Reaching low Earth orbit, LEO, requires a velocity of roughly 17,500 miles per hour, 28,000 kilometers per hour. This is already at the limit of what chemical rockets like the Saturn V or SpaceX Starship can achieve. On a super-Earth with 1.5 times Earth's gravity, the escape velocity increases significantly. The exponential nature of the rocket equation means that a standard chemical rocket would need to be impossibly massive, mostly fuel, just to lift a tiny payload. Biological perspective. The super-Earth is a paradise. It offers a thicker shield against cosmic rays, a more stable climate, and vast room for evolution. Technological perspective. It is a prison. A civilization evolving on such a world might be incredibly advanced, but permanently grounded, unable to launch satellites or explore their own solar system using chemical propulsion. They would need to develop nuclear propulsion or space elevators simply to achieve orbit. We have examined the super-habitable hypothesis from the perspective of a systems engineer. When we strip away our anthropocentric bias and analyze the raw metrics of planetary habitability, the data points to a clear conclusion. Earth is not the optimal model. Here is what the analysis reveals. Key finding 1. The stellar advantage. Our G-type sun is a high-performance but short-lived energy source. The K-type orange dwarf offers a superior operational lifespan, up to 70 billion years, providing the long-term thermodynamic stability required for advanced evolutionary complexity. Key finding 2. The geophysical sweet spot. Earth is geologically fragile. A planet with approximately 150% of Earth's mass ensures a longer-lasting molten core. This drives the plate tectonics and magnetic fields necessary to maintain a habitable atmosphere for eons, preventing the geological death we see on Mars. Key finding 3. The technological trade-off. While these worlds are biological paradises, they are likely gravitational prisons. The same physics that allow them to retain thick atmospheres would make chemical rocketry exponentially more difficult, potentially trapping civilizations on their home world. This is not purely theoretical. The Schulze-Makuch study identified 24 specific candidates from the Kepler dataset that fit these criteria. One prime example is KOI 5715.01, located approximately 3,000 light-years away in the Cygnus constellation. This planet orbits a K-type star. Crucially, its system is estimated to be 5.5 billion years old, about 1 billion years older than our solar system. If life exists there, it has had a billion-year head start on terrestrial evolution. While we still require direct atmospheric spectroscopy to confirm its surface conditions, the orbital mechanics and stellar parameters align with the super-habitable model. Looking ahead, this shift in understanding is reshaping NASA's strategic roadmap. The search is no longer just for Earth 2.0. The upcoming Habitable Worlds Observatory, HWO, a proposed successor to the James Webb Space Telescope, is being designed with these parameters in mind. By targeting K-type stars, we maximize our statistical probability of finding biosignatures. Beyond the specific astrophysics, this analysis teaches us a profound lesson about scientific humility. For centuries, we believed the Earth was the center of the universe physically. Then, we believed it was the biological standard. The super-habitable theory suggests that we are living in a starter home, a decent, functional, but ultimately temporary dwelling. Somewhere out there, orbiting an orange star, may lie the galaxy's prime real estate. Worlds designed not just to survive, but to thrive for eternity. Understanding the physics of super-habitable worlds forces us to reconsider our place in the cosmos. It suggests that while Earth is rare, it is likely not the best the universe has to offer. If you found this technical analysis valuable, I would appreciate your subscription. It helps support the research required for these deep dives. In our next video, we will address the engineering challenge raised today. Nuclear thermal propulsion. If chemical rockets cannot escape a super-Earth, could nuclear engines provide the thrust required to break the gravity trap? I am curious to hear your perspective on the trade-off we discussed. Would you choose to live on a biological paradise like a super-Earth, even if the high gravity meant your civilization could never leave the planet? Please share your thoughts in the comments below. Thank you for watching.